Okay. All right. So what are we doing today, right? What are we doing? Well, we're going to recap. Then we're going to talk about transfer functions and impedance. And then we're going to do problems if you have enough time. That's the plan. That's the plan. So residue, French now. Excellent. You guys forgot the X. Can't forget that you forgot the X. Anyway, residue is essentially the constant that you're solving for the partial fraction expansion. Right, so when we do partial fractions, we have like a over s plus b, b over s plus 2 plus cs plus d over s squared plus 4, right? So something like that. And a, b, c, and d are my residues, right? Another way of thinking about this is that when you're doing partial fraction expansion in the Laplace domain, what you are solving for are the constants in your differential equation, right? Whenever you would have an integral of something, go ahead and take it, you have plus c1, that c1 is the residue, right? That's A, B, C, and D are just the constants that we have in our differential equation, right? In MATLAB, it's easy, right? You type in residue, you give it the same thing that you give the transfer function function. That's a weird thing to say, right? The transfer function command, let's say, in MATLAB, right? You give it the numerator and the denominator, right? You give it the coefficients of the s squared, s, and s0, right? Same deal with residue, right? You give it the coefficients of your characteristic equation, and it will give you what the residues are. You guys have any other questions on that? Everybody started the homework, right? If you haven't, you should start it. That would be a good idea. A very good idea. Announcement about office hours before we start. Tomorrow afternoon, I have to cancel office hours. I have to go to a meeting from 3 to 5 instead of sit in office hours from 3 to 5. So office hours are still on today and Friday. Okay, from 3 to 5. Monday from 9 to 11 a.m. Right. Those are the rest of the office hours, the official office hours before the exam. If you need to meet with me or you want to meet with me or ask questions, right, you can always send an email. You can always see if I'm available at a time that you happen to be available, and we can try to meet at a different time, right? So just let me know if that works for you. So in the past 10 weeks, I want you guys to name 5 things. 5 things that we've learned. I mean, this is a deal, right? This is like half of a thing per week. Right? It's like half of a thing per week. And so 5 things that we learned in the last 10 weeks. Just in case anybody wants to get wise with me, saying nothing does not count. I'm talking about actual topics that we've covered. Transfer functions. Sure. We're going to do more with that today. All right, transfer functions. Someone from home. Someone from home. There we go. You can't say transfer functions anymore. It's already up there. Sean. Sure. We got chat. Heard state space. I saw IO equations in chat. I combined both of those. So state space. Equations. Time displacements. Dr. D's fabulous 5 steps solving problems. Jeremy, I think you mean time domain. I think you mean time domain, not time displacement. It's not an episode of Doctor Who. It's not like Cable from the X-Men, just displacement time. None of those things. Time domain responses, right? Good stuff. All right, so people have been paying attention. Great. So we're going to do more with transfer functions and Laplace transforms today. That's the whole idea behind impedance, right? State space, right? We can see where that's useful, hopefully, from homework 4 in the lab. Those are two places where state space is really nice, right? Input-output equation, literally everything that we do is an input-output equation, right? That's how we get the transfer function. That's how we spent the whole first 4 weeks of class, was writing input-output equations. And yeah, the 5 steps. Right? Dr. G's super terrific #1 5-step method for making models. Right? That's essentially the backbone of the class. Cool, cool. So if PowerPoint will do the thing, there we go. All right. So what are the topics for exam 2? Well, here they are, in case you guys were wondering what to expect, right? We have a little bit of modeling stuff that we covered, right? We covered state space and state variables, we covered transfer functions, and we covered linearization, right? We also covered time domain response analysis, right? So for first order systems, right, we want to know how do we characterize a first order system and how do we draw the first order response for a system. Right? That's where what we really want to know. For second order systems, what are the different root responses and what do they mean? What do you need to characterize a second order system? How would you go about drawing a second order system response? If you're given the plot of a system response, could you generate the model? Hopefully, yes. There's a whole homework question on that. Laplace transform. Right. So initial value theorem, final value theorem, and properties are all on the master sheet. Right,
Dr. D.
Yeah. So
someone's trying to join the video.
Oh. Right. So initial value theorem, final value theorem, and the useful properties of these Laplace transforms are all on the master sheet. Right. They're all there, and they're good to go. Inverse Laplace transforms, right, which typically result in a partial fraction expansion unless you get really lucky and you just have one that falls out directly into the form that you need, right? But anytime that we don't have a Laplace transform that falls into that category, right, that falls into a perfect identity match, right off the bat, we're going to have to do partial fraction expansion. All right, and then determine the system response using the Laplace transform method, determine the system response using the transfer function method, and impedance, right? 2 of those we covered last class, and the third one we're going to cover today, right? We're also going to do a bunch of problems next class, right? Today and next class that highlight a lot of these methods, right? And so when you're asked about the Laplace transform method, right? If you're asked specifically to carry out the Laplace transform method, which you are in the homework, right? And in other problems that we do, you are going to have to create the model, right? The Laplace transform model is create the model, apply the Laplace transform to both sides of the differential equation, right? So you Laplace transform the input and you Laplace transform the output. You then rearrange it and solve it algebraically for the output variable. And then you do the partial fraction expansion and you do the inverse Laplace transform to get y. Right? Those are the steps for the Laplace transform method. For the transfer function method, it's similar, but it's not exactly the same, right? In the transfer function method, right, we assume a 0 initial condition, right? So you're going to find your model, you're going to find the transfer function. Transfer function, immediately when you hear that, you say 0 initial conditions. Even if you're given initial conditions and you're asked for the transfer function, throw them away. Just use 0. Otherwise, it's not the transfer function, right? So you determine the transfer function in the general form, right? We'll talk a little bit about what that means in a little while, or when I say the general form. But in general, right, it's just the ratio of my output to my input, right? Okay. And you find that, and then you multiply your transfer function times the Laplace transform of your input, and then you do the partial fractions, and then you do the inverse Laplace transform. And then finally, impedance is the new stuff that we'll talk about today. Right? After today, you guys will have seen everything that's on homework 5, right? And next class is going to be us running problems, right? The ones that I gave on the sheet, if you haven't taken a look at the announcements from yesterday, right? I still owe you example problems. The reason I haven't posted them yet from last week is because we didn't cover all the ones in the PDF that I have yet. So I'll post them probably after class on, well, no, I'll probably post them after class today, because we'll have covered everything up through that then in the class today, and then the new problems I'll post at the end of the week, the ones for the sheet. Okay. Okay. In general, going over exam stuff, right? We're changing exam format a little bit. I'll go over it in more detail on Thursday's class, okay? But we are going to be taking it in test models. I know that some of you have some experience with that based off of the other professors that you've had. If you haven't, it's not a big deal. It's well, like I said, I'll go over the most of the specifics on Thursday, just so it's all fresh in our head for next week. But essentially, you're going to have to sign into a website with your student ID, right, to verify who you are. And you take the exam through this other website, right? The theory questions will get uploaded automatically. And when you're done with the exam, right, you just post your solutions to the handwritten part in LabCloud. Yeah. Fun. So it's not multiple choice. It's going to be like it was last time, right? A short answer. But all the short answer, you just type it into the web form, and you can go back. Like, it doesn't close out after you submit the answer. So you can always go back and jump around, but you just submit it there. So you don't have to upload the first page of the first 2 pages of the whatever the first 10 questions or whatever it was last time. But all the problems you still do by hand, and then submit them the same way you did last time in LabCloud. So the whole thing's gonna be through test models. Yeah. Yes, you're gonna see one question at a time, and you have to use next buttons to. Yeah. No, yeah. This I set it up so that you can jump around to whatever question you want at whatever time. Just don't hit submit, and you should be okay. Don't hit submit until you really want to submit it. That'd be my number one suggestion. Because the other caveat is you're only allowed to sign in once with your student ID for that particular exam. Yeah. Yes. It's gonna pop up on the screen. You will have a paper. You write your stuff. You work on the paper. When you're done, you take a picture. This is my phone. I take a picture and then upload it to LabCloud. So instead of downloading the exam from LabCloud, you are just going to have to do it by looking at your computer screen and writing down your work, and then uploading it the same way. It's just you can't download the exam. Okay. No, will the exam look closer to homework 5 or closer to homework 2 and 3 with added stuff? I mean, 2 plus 3 is 5, so, and this is a tough one. It's gonna look like homework 4 and 5, right? That's the content that's on it, right? I can still ask you modeling questions, but the goal of developing the model is that we can analyze it, right? So there's that, right? It's gonna look similar to the stuff that we've done in class. It's gonna look similar to homework 4 and 5. There's that. We can also next class we can talk about incentives. I won't call them bribes. They're not bribes. There's no quid pro quo here. Well, I guess there is because you have to do something to get it. It's an incentive, right? Think of it this way: like if you were an NFL player and you got like 500 tackles in a season, which is ridiculous, you'd get extra money, right? Um, so it's kind of like that, except that you get like a snack or like something else that happens, right? You guys know, you guys got ice cream sandwiches, so it worked out. Cool. You guys have any other questions? Like I said, we'll go more over Foster extra credit, huh? Once everybody gets all of the regular credit, then you guys can have extra credit. Okay? No seconds till everybody gets first. Okay? All right. Cool. We'll go over more specifics on Thursday, right? We can talk more about it if you have any questions about technology and things like that. But I will generate a slide that has specific instructions so that nobody is feeling like they're not prepared to do it because that would stink, right? The other thing that's nice about test models is the time doesn't start or end based on when I tell you it starts or ends. It automatically times you. So when you sign in and you get through all that stuff, that's when it'll start your timer for 2.5 hours.
If it starts the timer late, does that mean that like if we started the test a few minutes late, we'd still get the full time?
Correct. That is what that means. And then you get 30 minutes window after you're done to submit your work. No, shorter, 1 minute. Take your pictures really quick. Sean. The same thing that would happen if you were using LoudCloud, basically. Except I guess, so if that happens, use your phone to Discord message me, and we'll deal with that as it happens. Okay. So if that happens, if you experience an internet outage, right? Let me know, and we'll do that on a case by case basis. Okay. It's hard to make a blanket plan for something like that, but because I haven't thought about that. So I'll figure that out and we'll burn that bridge when we cross it. All right. Cool. Cool. Anything else? Anything else pressing that anybody wants to talk about? You guys have any questions or anything about stuff that we did last class that you want to go over? Yeah, Taylor. Yes. Good question. So, same deal as last time. If you are normally a Tuesday in-class student, you are more than welcome to come here into the classroom and take it if you want. If you have to be on campus for other stuff, that's fine. I'll be here, right? And you can do that, okay? If you'd rather take it from home, you can take it from home, right? So, I did have some students who were Thursdays last exam who decided to come into the classroom, and that's fine, right? So, if you come into the classroom and take it, right, make sure that you have to be a Tuesday student, right? Because I don't want to deal with the whole COVID protocols and contact tracing stuff in case something were to happen and you weren't supposed to be here and then, all that hits the fan. But if you're normally a Tuesday in class, feel free to come into class and take it or stay home if you want. Doesn't mean either way. You will get a lacrosse transform table, and you're allowed your master sheet, right, and your calculator. Right, those are the three things that you can have. The lacrosse transform table will be part of the exam itself. So there's that. Any other questions? You have any other questions? Everybody doing all right? All right, well, let's watch a video about Laplace transforms. Right? Let's also make sure that I have shared the sound on here. Uh-huh.
What is the Laplace transform and why do you need to study it? The Laplace transform transforms a function f of t in the time domain to another function, capital F of s, in the frequency domain. In the frequency domain, certain calculations become easier. So we transform our problem from time domain to frequency domain. We solve it, and then we transform back to the time domain. An excellent example for this is solving ordinary differential equations. You have looked at solving linear second-order differential equations of this type in the past. For homogeneous, meaning right-hand side equal to 0, second-order linear differential equation, the amount of work needed to solve when you do this in the frequency domain is the following. We take the Laplace transform of the whole equation, which is this. We know what the Laplace transform of 0 is, that's just 0. We know what the Laplace transform of this is, and also the Laplace transform of the second derivative, which comes to an equation like this, which we then simply solve for x of s, doing some rearranging of the equation. And we then transform back into the time space. And there is our solution to this initial value problem with a second order differential equation. Now that was an easy example because we were looking at a homogeneous differential equation. What if it is not a homogeneous differential equation? Take a look at this example. It is still a second order differential equation. It is linear, but on the right hand side we don't have 0. So if you were to solve this using the method you've learned before, you would find a general solution and you would find a particular solution and you would combine them to the solution. Now with the Laplace transform, we don't need to worry about any of this. Same as before, we simply take the Laplace transform of the whole equation. We know what all these Laplace transforms here are. We rearrange and in the end we've got our solution. Straightforward, without having to worry about particular solutions and general solutions. So this is much, much simpler. So what do you need to do to transform a function, little f of t, from the time domain to a function capital F of s in the frequency domain? Well, f, little f of t, and capital F of s are related as follows. Capital F of s is the integral from 0 to infinity of e to the negative st times our function little f of t dt. And this is also then written like that, Laplace transform of little f of t. Solve the integral and you have capital F of s. Often we don't need to actually solve any integrals as we have tables to read off the Laplace transform of a function. Here is an example of a table that we could use. For example, the Laplace transform of t squared would simply be 2 over s cubed without us having to calculate it every time we're looking for the Laplace transform of t squared. Now, transforming back from the frequency domain to the time domain, we also usually look up functions in the table. We just go the opposite way. So, for example, if we have the function 1 over s in the frequency domain, we know that this must be 1 in the time domain. So this was a very brief overview of Laplace transforms.
All right. Laplace transforms, right? Laplace transforms are helpful because they let us do differential equations with algebra. All right. So instead of having to go through the rigmarole of finding a particular and the wait for it, I'll get there, and the homogeneous solution, right? You can just you can just do some algebra, right? You take the Laplace transform, move some things around, take the inverse Laplace transform, and you're good. Okay. So last class they asked this question, and I thought it was a good one, so we're gonna go over it again. Okay. Some people were having some confusion when you have sines and cosines in your Laplace transform, right? So how do we take the inverse Laplace transform of something with sine, right? Or get something out that has sine, right? So I'm just gonna find So this is problem 6C from homework. 6C from homework 5, right? And we were given y of s is equal to 2s plus 18 over s squared plus 8s plus 20. Okay. And we're asked to find the time domain response of this particular transfer function. It's not a transfer function, but this particular Laplace transform. And we look at it, and the first thing we try to see is, does this match something from our table, right? Because we shouldn't just happen the partial fraction expansion. If it does match something on our table, turns out that it doesn't, right? But it does look like a couple of things from our table, right? It kind of looks like sine, damped sine, and damped cosine. Okay, kind of, but not really. So next thing we'll do is we're going to check the roots. So what are the roots of this equation? What do we get if we check the roots? What do we got? No. Negative what? Plus or minus 2? Close to. So first of all, it's not going to be 3, right? Because we've got s squared, so we've got to have 2. 2 roots, right? So you're close. Close. It's negative 4 plus or minus 2. Negative 4 plus or minus 2. So what do we know from this root response? What should we be expecting out of this? What is this? What do these roots tell us about? I heard underdamped. That's correct. And what is an underdamped? What does it look like? Harmonic oscillation is just a straight sine wave or a straight cosine. Yeah. So what do we call that? If you're so it's either going to 0 or it's going to grow. Right? So it's either going to decay or it's going to grow, right? So we have a damped sinusoid or a growing sinusoid, right? So we know from the roots that this has to be a damped sinusoid, right? This is going to have some sine component and some cosine component. And when we look at this, it looks like a combination of the sine, the damped sine, and the damped cosine Laplace transforms, right? Because sine of omega t times e to the negative at, if we take the Laplace transform of this, gives us omega over s plus a squared plus omega squared. Right? And cosine omega t e to the negative at, we take the Laplace transform, gives us s plus a over s plus a squared plus omega squared, right? From the Laplace transform, right? Just from the Laplace transform. So we're expecting that it will look like this, and we can see that this Laplace transform looks kind of like both of these, right? There's still it's not exactly like the cosine, it's not exactly like the sine. It's somewhere in between, right? It's somewhere in between them. So what can we do, right? Well, we're going to set up a partial fraction expansion here, right? But before we do that, we want to get our denominator such that it looks like the denominator of these two functions. Now, before we even do that, does this feel like cheating? Probably a little bit, right? Because Dr. D, what you're saying is that because you know what the root response is, you're just gonna force your solution to look like that. Yes, 100%. That is what I'm doing. I'm using what I know from other classes that I've taken that I know to be true to inform me about what the solution is engineering, right? You're using all of the things. We use all of the things that we know, all of the things that we learn to inform our solution, right? So because I know that this has to be a damped sinusoid, I'm absolutely going to make this look like a damped sinusoid, 100%, because the characteristic roots of the system tell me that that's how this is going to behave, right? So I already know the answer by looking at the roots. I just need to make my Laplace transform look like what I know the answer is. And to do that, I need this denominator to look like s plus a quantity squared plus omega squared. And the way that we do that is we have to complete the square on the bottom. Right, so how do we do completing this square, right? Let's review quick in case we've forgotten. Right, so if I want to make a complete square, right, a perfect square here. If I take 8 and I divide by 2 and then I square it, right, I'll end up with s squared plus 8s plus, we'll divide by 2 is 4 squared is plus 16, right? But that needs to be plus 20, so this is also plus 4, right? So all I've done is I've taken what I have here, and I've changed that 20 into 16 plus 4. Right, and the nice thing about this is that I get something that looks like that, right? This is black market math at its finest, right? It's what it is. S plus 4 squared, right? Well, that's s plus a, so I know a, and I know omega, right? And so this is nice because I've got a, and I've got omega, right? The problem is I don't know how much of this is the sine wave and how much of this is the cosine, right? So I still need to figure out A and B, right? What do I mean by that? Well, I mean, I know that this is going to break down into some omega over s plus a squared plus omega squared, right? Well, in our system, we know omega, right? And we know a. So a is 4 squared plus omega, which is 2 squared, plus the cosine component, right, which is s plus 4 over s plus 4 squared plus 2 squared. Right? So here we are. now we're here, and we've got really nice looking partial fraction expansion, right? Where we understand that this portion here is my damped sine wave, and this portion over here comes from my damped cosine. The question came up before, like, why is it a sine wave and a cosine? How do we know that it's both together? Well, we know that it's both together because the numerator doesn't look like either one separate, right? That's the really what it comes down to. The other reason is we'll talk about frequency response analysis, right? But typically when you have a sine wave that goes in, you're transforming it by some amplitude, and then you're phase shifting it. So the cosine is really just the phase shift to the sine. Correct, right? So the question was, if you had one that looked that matched up exactly to either sine or cosine, right? You would just use sine or cosine. Now, if you did this out and you thought it might be just sine or just cosine, the math will play out anyway, right? Because you'll get A or B as 0. So it should line up, right? It should line up.
Dr. D,
Yes.
should the original function be 2s plus 8? Or is it 18?
I got 18 in my notes. Is it 8 on the homework?
No, I just like looking at what you got.
Yeah, it's 18.
It is? Okay. Because like with if you like multiply the 2 times s plus 4, then you would get 2s plus 8. Right? Because then when you pull the 2 out.
If you pull the 2 out, you get s plus 9, right?
Yeah.
Yeah, if it was plus 8, it's just twice the cosine, right? If it was 2s plus 8, you would just use cosine omega t e to the negative 18. But it's
Okay.
not. Yeah. Oh, we're getting there. I was just giving everybody some time to write it down. Good question. Yeah. So what do we do with this now, right? What do we do with this now? Now we multiply through by the denominator, right? Because we're doing our standard partial fraction expansion. And the nice thing is that all of these things have the same denominator, right? Because they all have the same denominator, we end up with 2s plus 18 is equal to 2 times a plus b times s plus 18 times b. All I've done is I've taken this equation over here. I've taken this b, oh, it shouldn't be 18, oh, it's bs plus 4. Please hold. I don't know why I wrote 18. Dr. D, stop not looking at your notes and trying to do this from memory. That's so much cooler if you can do it from memory. Anyway. All I've done is algebra, right? B times s plus 4 is bs plus b4, or 4b, whatever you want to do. Okay, so I've got this. Now that I'm here, what do? I group the coefficients of my s to the 1 terms. I don't have anything higher than an s to the 1 term, so I don't have to worry about this. If you did, say this was bs squared, for example. It's not, but say that it was. Well, then you'd have s squared that 0 is equal to 4b, right? But we don't have that, so don't worry about that. So we have my s to the 1, right? So I've got 2. On the left-hand side, the coefficient of s to the 1 is 2, and that's going to be equal to b, because that's the only term that I have in front of an s on the other side. Well, that's nice. What about my s to the 0 terms, right? So anything that doesn't have an s. Well, I've got 18 is equal to twice a plus 4 times b, right? Well, this already solved b for me, so we're good here. I can take this and plug it in here, right? So this tells me that a is equal to 5. 2 times 4 is 8. 18 minus 8 is 10. 10 divided by 2 is 5. So a is 5, b is 2. Now we're good, right? We just go back, plug those into our original equation, and correct. So what we do now, right, is we say, well, I know y of s was equal to a times 2 over s plus 4 squared plus 2 squared plus b times s plus 4 over s plus 4 squared plus 2 squared, right? This is what I know. So I plug in a to a and b to b. All right, so that's where I'm left. Now I can take the Laplace, the inverse Laplace transform. Inverse Laplace transform of y of s is y of t. Yeah. The inverse Laplace transform of the first part is just 5 times sine of 2t e to the negative 4t. And the Laplace transform of the second portion is 2 cosine 2t e to the negative 4. And there it is. You can also get super fancy with it, right? I mean, like, you guys, this is really fancy. Watch this. Watch this move. Yeah, I did it. Crazy. Crazy. Right? You can pull that up if you want. Question. What's the time constant of this system?
One fourth.
There it is, 1/4. Nailed it. Why is it 1/4? Because it is the amount of time that it takes for us to decay by 36.8%, which is e to the negative 1. Look at this. And there, that's it. That's how we do that one. And we'll expect that everyone will get this one right on the homework. I'm just going to say that right now. I expect that everyone will get this one. If you don't, then we might have to have a chat after the fact. Do you have any questions on this? Right, so with sines and cosines and damped sines and damped cosines, right? Let the roots show you where you need, how you're supposed to form the solution, okay? It's not wrong, it's not cheating, it's what you should do. Always look at the roots, see what kind of responses you have, right? Always look at the roots. Any questions? We doing all right? You good? All right. Stop asking. All right, I'll stop asking. Geez. That's a blank slide. All right, let's talk about transfer function and impedance. All right, this is some good stuff, right? And I think you guys will like this because I know how much you all enjoy, circuit analysis and electronics, right? So I know that this is everybody's favorite. All right, so the transfer function can be found for any model in the same way that we have found it for a mechanical system, which is obviously we invoke the dark arts and then we get a transfer function, right? It's kind of like alchemy, right? The laws of equivalent exchange, all of those things. So we've been using basically all mechanical models in class. I don't know if you guys have noticed that since the last exam, right? Aside from a couple homework problems, we really haven't touched many thermal fluids or electrical systems, right? We've been dealing basically only with mechanical systems. But it turns out that you can apply the same things that we've been doing to any system, right? Specifically, the model for an electric circuit is still an ODE, right? And because it's still an ODE, we can still take the Laplace transform of it. And if we can take the Laplace transform of it, then we can do our Laplace transform and transfer function methods, right? So specifically, when referring to the transfer function here, we can create a model for our circuit. We can take the Laplace transform and then we can find the ratio of alpha. And that's how we find the transfer function, assuming zero initial conditions, right? Okay. So why don't we just do one? Why don't we just do one, right? So if I wanted to, so what is this asking us to do, right? For this RLC circuit, we want to find the Laplace transform, use the Laplace transform to obtain the differential equation of the model. And along the way, we'll also find some transfer functions. Okay. So this is a pretty fun circuit, right? It's got capacitor, it's got an inductor, resistor, it's got two voltage sources, right? It's got something for everybody. Something for everybody. Okay. So step one, right? You need a model. Now, this particular one doesn't specify, right? It just says to get the differential equation. So we'll do that first. Right. And then once we're done, we'll talk about how to find the transfer function. But it doesn't specify. Oh, it does. It says find it with regard to I3, right? Regard to I3, which you guys wouldn't know because I changed the picture, but this is with respect to I sub L. Okay. I3 is I sub L. Right. So we want to find the differential equation of the model for the current I sub L. Great. So where's my diagram, right? We'll draw a new one because we should always draw a new one and annotate it. And so here's E2, E1. We'll call this I sub R, I sub L, I sub C. Oh, hey, remember we've got a node here, right? That node's gonna mean that we don't have the same current in each of those branches. We also have what I'm gonna call my KVL. Right, so my KVLs are gonna go in opposite kind of directions, right? So this is KVL for the left-hand side. And this is KVL on the right, right? And this is based on the fact that I've got this voltage source here, and that's gonna swing voltage up and around counterclockwise, whereas the other one's gonna travel clockwise. Is it right or wrong to go? Doesn't matter, right? You guys know that if you chose it to go the other way, you would just be flipping the signs. That's all that would happen, right? You would get negative voltage, you get a voltage drop across ET and a voltage gain across EL and ET. Okay? Great, so we have our diagram. What's my input? What's my input? Yep, E1 and E2. What about my output? What do I have as outputs here? There it is, IL and E sub C, right? Because it's a circuit and we have both an inductor and a capacitor. Right, how many energy storage elements do we have? 2. What order is our system? 2, second order. So we're expecting at the end of this to end up with a second order ordinary differential equation, right? So at least we have that knowledge ahead of us, so we know that if we don't get a second order differential equation for the entire system, then we need to try something else, right? All right, so I've got my diagram, I've got my inputs and outputs. Let's write down our truths, right? Mathematical truths. Well, everybody's favorite mathematical truth, right? Is Ohm's law. It's everybody's favorite. We got EL is L, I dot L, and we've got I sub C is equal to C, E dot C. Right, I've got my KCL at node A, which tells me the current through my resistor is equal to the current through my capacitor plus the current through my inductor. I've got the right-hand side KVL. E2 minus EC minus EL is equal to 0. And I've got my left-hand side KVL. Tells me E1 minus ER minus EL is equal to 0. That's all of them. Right, that's everything that I need to start my reduction. And so let's do that. Now you can start with whatever equation you like, right? But what we do know is that we need one overall overarching equation in terms of I sub L for this entire system, because that's what we were asked for, right? We want everything in terms of I sub L at the end. I'm going to start with this equation, which is just my KVL from the left-hand side. Well, just rearrange it. Do you have to start here? No, you can start with the right-hand side. You can start with the KCL, right, if you want. It doesn't matter. You'll get to the same spot. It's just got to start somewhere. And I'm going to, excuse me, I'm going to start plugging things in here, right? First of all, I've got this. And that doesn't look super helpful up front, right? But if I plug in this, right? I plug in my element equations. Well, now I can plug this in here, right? So I'll get E1 is equal to R times IC plus IL plus L I dot L. Right. So I put the IR equation in, and that's great. But I can maneuver this a little bit, right? Because I have an equation for I sub C. So E1 is equal to R times C E dot C plus IL plus L I dot L. And I'm going to do some algebra, and I'm going to get all of my currents on one side and all my voltages on the other. Okay. That's what I'm going to do. So I'll be left with L I dot L plus R I sub L is equal to E1 minus R C E dot C. And I will call this equation 1. All right. Everybody all right so far? We good? Any questions? Been a while since we've done some circuits, right? Couple weeks. Probably a month. I know, like if I don't ride my bike for a month, I just next time I get on, fall right off. Don't even know how to do it anymore. So that's one, right? And we're gonna need another another first order equation to complete the set, right? Because we need two first order equations here. Luckily for us, we haven't touched that KVL for the right-hand side yet, right? So why don't we start there and see what happens? Put a dash there. So we'll end up with E2 is equal to EC plus EL, right? And this is KVL from the right-hand side. Well, I like that. I like that one quite a bit because I've got E2 is equal to EC plus L I dot L. And that's it. That's everything, right? Because in terms of IL, EC, and E2, which are all input and output variables. So just leave it. So we've got a couple options here, right? Because I want one single unifying equation in terms of I sub L, right? So either I have to solve for E sub C, like solve equation 2 for E sub C, and then take the derivative of E sub C so that I can plug that into the E dot C equation, which is not impossible, right? We could do that. But that gets kind of gross in situations outside of like this nice second order system, right? That's not really what we want to be doing. So I'm going to rewrite these two equations on the next slide so we have it. Okay. So we've got equation 1, where are you? Yeah, L I dot L plus R I sub L is equal to E1 plus C E dot C, 1, and E2 is equal to EC plus L. All right, so for this particular one, it's not that bad, right? We could take the derivative, right? Take the time derivative, slap them in there, right? If we want to do it the other way, that's when it gets gross, right? Because if we wanted this in terms of E sub C, then we'd have to take the integral of I sub L. So like plug that into the next one. So. Yes. That should be minus. Thank you. Thank you. Is it minus? Hold on. Double checking. It's plus. Yeah. I've been making a lot of algebra mistakes today, guys. I apologize. Apologize. Okay. So we've got these two equations. And yes, we could take the derivative of it. And I'm not going to do it that way, though, right? Because why? Because we just finished learning Laplace transform, so I'm going to flex and do Laplace transform, right? So let's take the Laplace transform of equation 1. And if I do that, right, well, remember, I wasn't given any initial condition information, so I'll just assume that there's 0. It's a circuit. It's probably going to be 0, right? Probably. It makes most sense that it would be off, and then we would turn it on. If you're not given initial conditions, assuming 0 is fine. And if we assume 0 initial conditions, right, I can take the Laplace transform of this. Well, equals plus R. One of S. Try that again. RCSE of S. So I end up with this. So where'd that come from? Well, in general, remember that if we take the Laplace transform of the first derivative of a function y of t, right? This results in s times y of s minus the initial condition. That's the first derivative property. Well, in this case, we said we have 0 initial conditions, right? So that goes away. We're just left with s y of s, right? Which is this part right here, which is this, right? S times IL of s. That's what it is. So I'll combine my like terms, right? So I'll get LS plus R, which I will now be calling laser for the remainder of the problem. Laser times IL of S. I'm in. Okay. We're done with this one for now. I'm going to call this now L1, equation L1 for Laplace form. Because why not? And I'm going to take the Laplace transform of equation 2. Right? If I take that, equation 2, right, I'll end up with E2 of S is equal to E C of S plus L S I L of S. Okay, so what should I do now? What should I do now? Well, one equation in terms of IL. So I'm going to solve equation 2 for E sub C. I'm going to plug it into equation 1. So this EC of S is equal to E2 of S minus L S I L of S. And this is what I'm going to call equation L2. We'll take that, throw it into equation L1. Right, so take this and put it right there. Let's take a look at that. I've got everything in terms of IL, E1, and E2. Yeah, so we are pretty good to go. So what now, right? Well, I'm going to bring all my ILs over to one side and leave everything else on the other, right? Because that forms my input-output equation, right? If I have all my inputs on the right and all my outputs on the left, right? So I have all my ILs on the left and my E1 and E2s on the right, then I have an input-output equation, right? So let's write that on the next slide. I'll get there. And if I do that, we get that. Right? Do this, you get this. Now look at that. That's a second order equation on the left-hand side, right? Some people might even say that that's the characteristic equation. Some people. But we weren't asked for that, right? We were asked to get the differential equation that combines these two sides in terms of IL. And so we can do that, right? How do we do that? Well, we multiply through by the IL, right? Because remember, the S term in the Laplace space is the same as the derivative, right? Remember when we did time domain transfer functions? Yeah, and we plugged in the D operator, and D squared was just DDT squared, right? Well, that's the same as S here, right? S is just my time derivative. So I can rewrite this as LC I dot L of T plus L I dot L of T plus R I L of T is equal to E1 of T minus R C E dot 2 of T. Now, you'll notice this should be a double dot here, right? Now you will notice that I still use a capital I for current here. That's because writing this for I dot it looks stupid and I don't like it. So I don't do it. Oh. So hey, look at that, a second order ordinary differential equation in terms of IL and my inputs, right? Great success. Now, for this case, right, it doesn't seem too bad if you wanted to do it the other way in the time limit, right? But I think that we've done sufficient examples where doing this in the time domain would be pretty laborious and kind of gross. So doing it in the Laplace domain allows us to use straight algebra to combine everything together. And then when we want to pull it back out to see what the differential equation was, we can do that as well. So let's talk transfer function. Right? Well, first off, you guys have any questions? You guys have any questions? No question. Everybody's good. Oh, yeah, of course. Okay. So I don't want to say this. All right. So we know that, right, in general, right, we know that right? If we take the Laplace transform of this, right? This is equal to s squared y of s minus s y of 0 minus y dot of 0, right? That's the general for a second, right? So if I wanted to take the inverse Laplace of this, right, where I know my initial conditions are 0, this just becomes, instead of writing it like that, which is sloppy and gross looking, right? With this. So if I wanted to go back when I know the initial conditions are 0, the inverse Laplace is just going in this direction, right? So that's the missing step out of it, right? So we're just inverse Laplacing that equation I'm getting. And that's why the transfer function method is nice, right? Because if you use 0 initial conditions, you can just pull that back out without any issues, right? I mean, you could do it with non-zero initial conditions as well, right? But sometimes it becomes a little bit tricky. They'll manifest as constants on the record. Let's talk about the transfer function. Let's talk about the transfer function. What if I wanted the transfer function here? How would I find it? Well, how many transfer functions are there in this system? Let's start there. What do you guys remember about number of transfer functions? We haven't talked a lot about it. Definitely have mentioned it though. How many transfer functions do you have in general? What is the transfer function? Let's start there. What is it? What is the transfer function?
Is it outputs over inputs?
Yeah, it's the ratio of your output to input. And Trevor, I'm the one who asked the questions here, not you. So
Huh.
the ratio of your output to your input. Yes, that's not entirely true. I do ask you guys to ask questions all the time. So sorry for being rude. The ratio of your output to your input, right? How many outputs do you have? Overall, for the entire system, how many outputs do you have? 2. How many inputs do you have? 2. How many transfer functions should we have? 2 times 2. You have 1 for each input-output pair, right? So you have a transfer function for IL with respect to E1 and E2. You have a transfer function for E sub C with respect to E1 and E2. This particular equation allows us to get the transfer functions for I sub L. If we wanted the E sub C transfer functions, we would have to have solved this in terms of E sub C. Okay. So if I want the transfer function here, right, we're going to use this equation up here, this red dot, right, to talk about transfer function. I'll just rewrite it right here. LC S squared plus LS, or LCS squared plus laser, ILS equal to E1 of S minus RCS E2 of S. Okay, I want the transfer function here, right? So I have to do it 2 ways. Now, I think we talked about this too, but just to cover it again, the way that you do this with multiple inputs is you ignore the contribution of one of the inputs. You set one equal to 0, and you find the transfer function with regard to the other part. So we'll start by saying E2 is 0. We are assuming that both of these are independent inputs, right? We're assuming that these are independent inputs and that you can turn them on and off independently. That's what independent means, I guess, right? So I'm going to set E2 is equal to 0. If that's equal to 0, and what you can't see, anybody except me, because the screen doesn't transmit to the board or anything, but I'm covering up the E2, the RCE2 part, right? What am I left with? Well, I want to find the ratio of IL of S to E1 of S, which is just going to be 1 over LCS squared plus LS plus R. And there is my transfer function with regard to E1. Now, if I hold E1 as 0, right, I can find IL of S over E2 of S, which is negative RCS over LCS squared plus laser. So before, at the beginning of class, when I said you want to keep your transfer functions in the general format, this is what I meant. We're not going to take the Laplace transform of E1 yet. We're finding the transfer function. The transfer function doesn't care what your input is, okay? It doesn't care at all. Okay, you could have E1 of t is equal to 25 volts and E2 of t is equal to 5t volts. You could have these inputs, and that's great. It doesn't matter yet because we're finding the transfer function, and finding the transfer function means that this will work for any E1 and any E2. So if you were asked to do the transfer function method, do not take the Laplace transform of your inputs until you are ready to multiply your transfer function by your input. Because we can take the Laplace transforms here, right? This just becomes E1 of S is equal to 25 over S. And this one, this becomes E2 of S is equal to 5 over S squared, right? So from the table. And we can do that. But it doesn't matter. When you ask for the transfer function, keep it as output over input, right? We don't care what the function is. Don't substitute it in early. Don't do any of that. Just leave it like this. Because if you substitute it in early, it's going to mess with your system dynamics because you're going to end up with an S in there somewhere that you're going to forget, that you're either going to forget to take out or you're just going to multiply it straight through and not care, right? And it's going to throw it off. So when you're finding the transfer function, leave it general until it's time for you to multiply your transfer function by your specific input and then go. The other thing is, we've got our characteristic equation in the denominator here, right? And that's great. That's great. And if you had done this, so that's the characteristic equation. If you had solved this equation in terms of E sub c instead of I sub l, what would the characteristic equation look like for that? What would you expect? Remember, the characteristic equation tells us about the natural dynamics of the system. It should be the same. You should get the same characteristic equation whether you solve this for one input or the other. The numerators are going to change, right? Your E1 and E2 are going to change, right? But the characteristic equation remains the characteristic equation. Right. Do you guys have any questions? Right. This is important because I have noticed empirical evidence has shown me that somebody will plug in the Laplace transformed input before you take the transfer function. and it will mess things up. So let's buck the trend. All right, let's be prepared. Mhm. Transfer functions are powerful, right? Why are they powerful? Because they allow us. Right, so what if you wanted to solve for the response here, right? Multiply your transfer function by the input, right? Do your partial fraction expansion, inverse Laplace, you're done. Right? You can do that. You don't have to do that for this problem, but that would be the steps that you would take. You guys have any questions?
So what would this look like if we put it in Simulink? Would we put two transfer functions in with Simulink? Like, I'm just confused as to what that would look like.
If you did it in Simulink, I would use a state variable, well, not state variable. I would use the integrator block method
Oh,
for that equation and have two separate inputs, right, that make up my other input that equal my IL times S, right? So I'd solve it for ILS, right? So you end up with essentially the two transfer functions, right? They're just going to be subtracted from one another, right? Which is okay. Any other questions? Okay. Let's, so let's talk about impedance one. Okay. So it might surprise you to know that resistance impedes the flow of current, right? It stops the flow of current, right? It slows it. It impedes it, right? But it turns out that capacitors and inductors also impede the flow of current to some point, right? So in an electrical system, impedance is the generalization of the ratio of the voltage transform to the current transform, right? The Laplace transform of the voltage and the Laplace transform of the current. And it is given the symbol Z, right? So we can see here that Z is equal to V of S divided by I of S. Does this equation look similar to any other equation that we have used in the past?
Ohm's law?
Ohm's law, 100%. It is Ohm's law, right? Look, if I rearrange this, right, I've got my voltage is equal to some impedance times I of S, right? Okay. So it looks like Ohm's law, right? So the impedance of a resistor. Let's go through this one, right? So I've got E sub R is equal to R I sub R, right? This is in the time domain. So I'm going to take the Laplace transform of this, right? And I get E R of S is equal to R times IR of S. But it's not impedance yet, right? Because impedance is the ratio of my voltage to my current. So I can make that happen, right? Voltage of S over current of S is equal to R. So the impedance of my resistance is just my resistance. Right, so essentially, where do these come from, right? We can normalize these elements based off of Ohm's law, right? And we're going to use our elemental equations and just take the Laplace transform of them and solve for E of S over I of S, right? Okay. Okay. So that one was easy, right? What about the impedance of a capacitor? Close, close. So let's run it. Let's run it through, right? I've got I C of S is equal to C. Well, it's not of S yet. Sorry. I C of T is equal to C E dot C, right? I take the Laplace transform. I C of S is equal to C S E. There's no dot. Capital E of S. E C of S. Right? One over C times S. You guys do the next one. Tell me. You guys find out the impedance for an inductor based off of the elements equation. Based off of the elements equation. I gave the other class this. Only fair. Should start with this. Start with that. If you didn't already start with that, start with that. If you did start with that, then I'll drop off. Take care of it. Like another minute. All right. What we got? What we got? What was that, Sean? Yeah. So what's the answer? What do you got? LS. All right. We got some LSs. Do people agree or disagree? All right. Most of the people in class are giving a thumbs up. If you're at home, thumbs up for you agree, party hat for you disagree. Because there's no negative emojis in Zoom, which is really, something I've never read them a lot about. Yeah. Okay, so everybody's got LS. Good, because it is LS. Great job, everybody. All right, so how do we do it? All right, take Laplace transform. EL of S is equal to LS, IL of S, right? EL of S over IL of S is equal to LS. Let's make it official. There it is on the PowerPoint, right? Since He typed it in Times New Roman. It's gotta be true. It's not really Times New, that's the. Is there? Yeah, might be. I don't remember anymore. Blake. No. So the thing about impedance, right, is that, and for most circuit analysis, right, we tend to have zero initial conditions to begin with. But this is not a transfer function, right? And it's not, so I guess to answer your question, it assumes zero initial conditions to begin with. And if you don't have zero initial conditions, you're probably not going to be trying to do impedance anyway. But most circuits do tend to start off and then recover them. Most. You can also extend impedance, the idea of impedance, to mechanical systems somewhat. It's a little bit different. But you can kind of, but we're not going to really talk about that. Just so you guys know, I forgot to mention it when we started, none of the stuff on impedance is in your textbook, okay? But there is a support document in LoudCloud in the path, like one of the study material documents that does have stuff about it. Okay? Does have stuff in it. Also, if you guys know Dr. K, go to his office hours and ask him all about it. He loves impedance, one of his favorites. I mean, I guess you can come to my office hours too, but. Yeah. All right, anyway. Everybody good? All right, we've got R, 1 over CS, and LS. But why? Why do we even care, Dr. D? What is the big idea with impedance? Well, Jerry Seinfeld getting there. All right, so why do we care? Well, it's useful because we can combine individual impedances in series and parallel, right? And the way that we do this is we use the resistor rules, right? Because why? Because everything was normalized using Ohm's law. So, excuse me, if we have impedances in series, we just add them together, and that is our equivalent impedance, right? When can we do this? When the impedances in series have the same current going through them, okay? What about if they're in parallel? Well, then we use the reciprocal rule. When is that appropriate? When the impedances have the same voltage drop. When the impedances have the same voltage drop. So why don't we just give it a shot? Why don't we just give it a shot? This is a circuit. Looks like a circuit. So what should we do here? Well, normally, if we weren't going to be using impedance, right, this one kind of would be somewhat of a pain, right? Because, well, I've got nodes in a couple of spots, so we'll draw it. We'll draw it anyway. Let's draw it anyway, right? So this one's got a couple of things about it that are different than we normally do, but we're going to talk about it in a second. Okay, so what were we asked for? All right, we're asked to use the impedance method to obtain the transfer function, right? E out over ES, right? The output over the supply voltage for the circuit shown in this figure. Right, and that's different than normal for us, right? Because normally we are talking about, we have IL or E sub C as my output, but this is very specifically stated that we want to know how much output voltage we are getting, right? Those are just terminals, right? So imagine you've got a resistor there, you clamp on your alligator clips, and you're reading out the voltage across that. That's what we're doing. And normally this would be kind of gross, right? Because we've got a node, oh, that was wrong. We've got a node here that I'll call A. I've got a node here, B, right? I've got some current IR2, some current IC, right? This is going to have some current I sub B, right? We'll have some current coming in here, I sub A, right? And I mean, it's not impossible. We could do this with our standard Kirchhoff law analysis, right? but it's kind of gross. So let's continue on, right? So we've got our inputs, we've got our diagram. Our input's going to be E sub S, and our output is going to be E sub out. Why? Because that's what we were specifically told. That's what we need. So I've got my diagram, I've got my inputs and my outputs. Now we got to write down our mathematical truths in this. Okay. So mathematical truths. Well, it's a circuit, right? So normally, if we were doing this in the time domain, we would write down, our Ohm's law, right? But we're not. We're going to try this with impedance. Well, that's kind of like Ohm's law, right? Because Z is just E over I, right? It's kind of like Ohm's law. And we have our capacitor, right? So we have 1 over C times S. That's nice. We don't have an inductor. There is one other thing, though. I am going to write here. That my output voltage is going to be equal to my resistance, R1, times the current through that resistance. And that's just Ohm's law right now in the time domain, right? Or sorry, in the S domain. And that's really all that we need to do. Because here's what we're going to do. I think we will all agree that this section here is really messing everything up, right? Really not cool. I would really appreciate it if this section would just go away. So I am going to make an equivalent impedance that I'm calling ZEQ1 out of this parallel subsystem. Now, is that okay? Based off of the rules that we had, right? As long as they have the same voltage drop, then that's fine, right? I can collapse them. And they do have the same voltage drop, right? Because they're in parallel. They don't have the same current, but they have the same voltage drop, which works out for us here, right? So let's start there. Sean. No, you don't need to write that down. That's fine. If you wanted to, it's fine, but it's not required. The question, in case you guys didn't hear at home, was do you need to write down the laws for combining impedances, right? And the answer is no. You don't need to write them down as the truth, but you're going to use them, so you're going to have to write it down eventually, right? So we've got two things in parallel. 1 over Z EQ1 is equal to 1 over Z R plus 1 over Z C, right? Which, well, this is 1 over R plus 1 over CS. Or 1 over R plus CS. Because 1 over puts it back up to the top. Now that's great. That's great. And I should really make this R2, right? Because that is R2 in our diagram. We have two resistors, R1 and R2. We can't assume that they are the same. Great. But this is, I don't like the way this looks, and I'm going to create a common denominator, right? Just to refresh, how do I do that? I'll multiply this term, the CS term, by R2 over R2, right? Why? Because it's multiplying by 1. It doesn't change anything about it, right? Multiplying by 1. But I can now combine these two things here, right? And so I'll get 1 over Z EQ1 is equal to R2 CS plus 1 over R2, or when I find ZEQ1, R2 over R2 CS plus 1. Now that's interesting. Right? Why is that interesting? Well, that looks like a standard form first order equation in the denominator. Right? So if you know the standard form first order equation, what is the time constant for this? If this was the system, what is the time constant for this impedance? What is, how about this? Let's start here. What is the first order form, standard form for an equation? What is the standard form of a first order equation? Let's start there. Yeah, that's good. Yeah. Closer with that one. So first order equation. What's the standard form? This is something like, look on your master sheet. It's on there for sure. I know it's on there. What's the first order standard form equation? Yeah. Right. Tau y dot plus y equals whatever. Don't really care about that for right now. AUT, right? So based off of this, what is the time constant? Not -1. Close. Yeah, halfway there. What if I rewrote this as it's R2 times C, right? All right, so let's talk about this. This is an idea. This is an idea here, right? So if we were to rewrite this and we got on an equation for this, right? This would be R2C times some variable. In this case, it's going to be E dot plus E, right? Tau y dot plus y. Yeah. This time constant has to be everything in front of the dot, okay? This is important because for a first order system, we can quickly and easily identify the time constant if it is in first order, standard form, right? Yeah. All right, but anyway, not really here or there for this problem. That was a tangent. Right? Side quest complete. All right, so we've got this, right? We've got this is my ZEQ. So I can rewrite or redraw my circuit now, right? And I'm going to use ZEQ, right? ZEQ1 is just going to be represented by a resistor. And then I've got this other resistor down here. And this is R1. And here's E out, ES. This is my new circuit here. And that's great. Why is that great? Because now that I've collapsed this is a single loop system, right? So that's just the same currents, right? They are in series with the same current. So now we can collapse this again. We're going to collapse this again. Right? We're going to do another ZEQ, but this time in series. Another ZEQ this time in series. So ZEQ2 is equal to ZEQ1 plus R1 plus R1. And we just found out that ZEQ1 was R2 over R2 CS plus 1 plus R1. All right, so once again, I'm going to do my common denominator here, right? So I'll get R2 plus R1 R2 CS plus R1 over R2 CS plus. I didn't do that one out, right? What did I do? I multiplied both sides. Or multiplied R1 by R2 CS plus 1 over R2 CS plus 1, right? Multiply through and drop that. Right. So here's the thing about ZEQ2. This is equal to my supply voltage divided by my current, which is not what I was asked for, right? I was specifically asked for E out over ES, right? Up here in the corner, this guy. Right, up there with the colors. Okay, so that's for that, but that's not that, right? So how do I get here from here to there, right? Well, I know I, kind of, but I need to get I in terms of E out, right? And luckily we have that. Because we have this, right? We know E out, right? So in the beginning, we know the voltage drop here. We know this voltage drop. We know that voltage drop. So if we know that voltage drop, it has to be proportional between R1 and I sub S. We can rewrite this and say that I sub S is equal to E out over R1. Right? And that's important. That's important because that ties it all back together, because I'm going to plug that in the equation I have on the next slide, right? So let's look at this, right? Remember, I've got I of S is equal to E out over R1. And I'll plug that in here, right? So ZEQ is R2 plus R1 R2 CS plus R1 over R2 CS plus 1. This is equal to E sub S of S. It's E sub S, not E times S. E sub S of S over E out of S times R1, right? Because E out 1 over E out over R1 is just R1 over E out, right? So, everybody okay with how I wrote that? You all right? Yes or no? Fine. So I divide, right? And get ES over E out of S is equal to R2 plus R1 R2 CS plus R1 over R1 R2 CS plus R1. And we're close. We have ES over E out, we need to flip it. So now we flip it. We did the long one. And there it is. Right, so how are we supposed to know, right, that we need to do that? So remember, what is impedance? Impedance is the ratio of voltage to current, right? You're asked to find the ratio of voltage to voltage, like the transfer function we just had to find. You're probably going to need to convert that current into one of those voltages. So think about what it is that you have and what it is that you need. Okay? You guys have any questions or questions? Any? Okay. Questions? Anybody? Doing okay? A lot of algebra, right? A lot of algebra. So for these, right? Because in the past I've told you guys not to get crazy with all the simplification and stuff, right? And for these, you can see how it gets pretty intense algebraically pretty quickly. I mean, in terms of partial fractions and things, you have to be pretty strict with how you do your algebra, right? You've got to make sure that you're finding roots. You have to make sure that you are accounting for all the responses. For stuff like this, right? If you don't simplify it all the way, it's not going to look nice. But that doesn't mean that that's wrong. Right? So get it as far as you think you can comfortably. Would be my suggestion. Right? That's what I would say. So, all right. We've got some time. If there's no questions. Very good. I'm gonna draw a picture for you guys. It's gonna be really good. Okay. So here's a picture for you guys. I hope you like it. What I would like for you to do is take the next 15-ish minutes, next 20 minutes. Yeah, 20 minutes. We'll take the next 20 minutes until 2:45, and I want you guys to solve this using the impedance method. And I want you to find, here's what you're going to find E out of S over I of S. That's what you need to find. Mhm. So. Resistor. You want three of them together. What? You do all three of them together. Double check that. You guys at home have any questions? You've got a little extra time. Try to figure out the differential equation that this creates, or that this came from. right. It's been about 15 minutes. You guys want some more time? Want the extra 5 minutes? Yeah, okay. How you guys doing at home? You all right? Andy, you guys have any questions? No? Okay. All right, I think we good. Everybody good? I guess technically I offered you 2 more minutes. You can take it if you want. Well, everybody's okay? Let's go. Yeah, go for it. Okay. All right, guys, that is the time now. Let's get back to it. So, what do we do? What do we do? This is you're given this. You want to find that thing. What do we have to do? What do you guys think? All right, let's start with since you already drew the diagram, presumably. Input. What's my input? Yes, IS. What's my output? Yeah, excellent. Okay. Mathematical truths. What are we rolling with? Mm-hmm. Mm-hmm. ZR is equal to R, ZL is LS, and ZC is 1 over CS. Perfect. So if we have that, right, and we know that, and we understand that these are all going to have the same voltage drop, right, because they're all in parallel and they're all referencing the same ground. So because we know that, we can use our parallel rule, right, and we can smush these all together like an accordion, right? And if we do that, we'll end up doing a reduction, right? 1 over ZEQ, 1 over R plus 1 over LS plus CS, right? So I do my common denominator here, do that. Okay. And then if you find ZEQ, you found the answer, right? Because you needed E out to I of S, and that's what Z is. So we don't need anything else. We don't need to map anything else to anything else, right? So be cognizant of what you're being asked to find, right? Because you could potentially try to make this something that you weren't asked to find, right? And waste time that you could have been spending doing other things, like playing Among Us or, you know, things that matter to real life. All right. Yeah, well, no, I did. It's okay. Okay, we'll have plenty more opportunities. But the second part, right? If you wanted to make this into a differential equation, right, what would you do? Cross multiply them, then take the inverse cross transform, right? And so you end up with this second order differential equation in terms of the output voltage and the input voltage. And there shouldn't be an S in there, by the way, because reasons. It should just be fine. Now, if you wanted to, you could double check this, right, with actually doing the circuit with Kirchhoff. And this one's not too bad. It's just super repetitive when you go to do it with Kirchhoff. You will see that some of the problems that you will do next class are going to be problems that we've already done, right? But we're going to extend them and try to work through them fully. Now, I know what all of you are thinking right now. You're like, this is great. This is great. But does it work for op amps? I know that's what you're thinking. And actually, it's a great question because, wait for it. Because it does. It does work for op amps. It does. You can totally do this with op amp circuits. It's totally cool. So we'll do this problem real quick, and then that's going to be it for the day, and we'll catch up with the problems that are on the worksheet that I posted, right? But, so we're going to do this, right? So let's draw it out, right? So I've got my E in R1. R2, C, E out. Right, just trying to make it look like something that we've seen before, right? That's EB, EA, IA, IR1. Call this current up here IC. All right, we'll say that this is IR2 coming out of there. Well, I guess that's IC, right? So that wouldn't matter. That's IC. Okay, cool. So it's something that we have, right? Obviously, with op amps, our input is E in and our output is E out. And what we're being asked to find is the transfer function here, right? We want the transfer function of our output voltage to our input voltage. Great. So, we've got our mathematical truths. And in this case, right, we still have the same mathematical truths that we've always used for op amps, right? And if you were to take the Laplace transform of these, right, these just become EB minus EA, right? And so we can say that EA, capital EA, has 0, right? Just taking the Laplace transform, it's not going to change it. Taking the Laplace transform doesn't change the difference between the two terms, right? Because it's a linear operator, so it wouldn't do that. We're going to do this with impedance, though. Because as much fun as it looks like trying to figure out what the voltage drop is across a resistor and a capacitor in series, I'd rather just use the impedance to figure it out. Yes, 1 over CS. Thanks, Sean. 1 over CS. And we do have KCL here at A, which tells us that IR1 is equal to I sub C. Because IA is approximately 0. All right. So everybody's cool with this, as I've written, right? I know, again, I know op amps is everybody's other favorite, right? And then we hit all of the favorites here. Yeah. There's a buffet of your favorite topics just waiting for you. All right. So what do we do? All right, we're going to do a reduction. Well, if we're going to use impedance to do this, it's actually not too bad. So the first thing I can write is, well, I know that my input voltage minus EA of S divided by IR of S is equal to R1. Right, we know that already, right? The voltage drop divided by the current is equal to the resistance. But we know that that's 0. We also know what? Well, we also know that E out, well, let me write it this way. The voltage drop EA of S minus E out of S divided by the current I sub C of S is equal to what I'm going to call ZEQ, or the equivalent impedance of the series resistor and capacitor. Okay. This is also 0. So now we just need ZEQ, right? Well, ZEQ is R plus 1 over CS, or if we rewrite it, I guess this is R2, right? Because that's where we're at. This is R2 CS plus 1 over CS. It's not a K, it's a C. CS. But we know that these I's are the same, right? This and this are equal by KCL, right? They're equal because of the KCL. And since they're equal, I can solve one in terms of IR and plug it in to the other, right? So which one do I want to solve here? Right. Well, I'm going to say that I sub r is equal to EI of S over R1. And I'm going to plug this into this equation. So I'll get negative E out of S divided by E in of S times R1 is equal to ZEQ, but ZEQ is just R2CS plus 1 over CS. Solve this as such. And there we have it. So when we have really complex, we have elements that are not the same, right, built in series or in parallel around our capacitor, we can use impedance to squash them, right? Particularly useful when we have a bunch of parallel branches that we can then collapse into two series impedances and then move those together. That's how it works, collapsing together. Is there any questions? Now you guys have everything you need to do all of the homework 5. That's everything for homework 5. Next class is us doing problems and answering questions. That's what next class. We're not going to start anything new before Thanksgiving. We get back from Thanksgiving, it's all frequency response stuff. And a mad dash to the finish because there's still lots and lots to do everywhere. Right? That being said, for participation this week, due by Thursday at 11:59. I have decided that I deserve my own signature meme, something that I feel like I've earned, and you guys are going to make it for me for participation. One entry per team. On Friday, there will be judging by Professor Comfort, Professor Price, Dr. Skies, and Dr. Wright. I feel like they've agreed to it. I don't know if they've actually agreed to it, but it's fine. Don't worry about that. They're going to choose a winner from each section. The winning team will get 5 practice points. One submission per team. Please keep it PG-13 tops. Okay. Okay. Whatever that feels. I'm not going to hinder your artistic meme process. It's not what I'm about. So, all right, cool. That's it. That's for today. Dr. G, this assignment doesn't have anything to do with engineering. It's true, 100%. No. No.